Hi, this video is about sketching curves, graphing, doing the graph of an equation using some of the basic elements of a graph. I'm following James Stewart's calculus textbook, and in that textbook, this is chapter 4, section 5, but you'll find this helpful in any textbook, I think, on calculus. So first of all, what is the domain of the function? So what are the set of values for which the function is defined if it's a function? The chief concern, in my amateur graphing, the chief concern is not to divide by 0. You can usually tell right off the bat a number that's not going to be in the domain of a equation or a function if it's in a rational form, x over y or something like that, something over something, that is. And you don't want the bottom to end up to be 0. So that's the main thing when you're looking for the domain. Of course, intercepts. Finding the intercepts is another key part of doing a graph. So if you want to get a y-intercept, set the x equal to 0. Again, it's the opposite. If you want the y-intercept, set x equal to 0. If you want the x-intercept, set y equal to 0. So if you want to find the y-intercept, set x equal to 0 and see what comes out. And if you want the x-intercept, set y equal to 0, and then you're going to have to solve. James Stewart's textbook says basically if this is going to be too involved, it's not worth it. Just, plot some points. Symmetry. So we have find the domain, find the intercept, symmetry. So there are basically 3 kinds of symmetry. If you plug in negative x to the function and it ends up the same as f of x, then there will be symmetry about the y-axis. We said this in an earlier video. The idea here is that you have the x on both sides. We call this even symmetry because usually, and this is a new thought, usually it happens when the powers of all the variables are even. I didn't know before doing this video or before reading this why they call it an even function. But I think this is why. It's an even function because if it's a polynomial, all of the variables are going to be raised to an even power. Or a constant. And so you're going to have y-axis symmetry if you have even polynomials in terms of the powers and constants. Okay? Symmetry about the origin is if you plug in a negative value of x, you're going to get a negative value of y. In other words, if you plug in the negatives of both x and y, it comes out with an equivalent equation. Then you have symmetry about the origin. And this is called an odd function. And again, I didn't know this until I was getting ready for this video. This is called an odd function because if all the powers of a polynomial are odd, no constants for this one, then it's going to have symmetry about the origin. So if you had x to the third power plus x, and you were asked to graph that, it would end up having symmetry with regard to the origin. Some other symmetries. So if the graph repeats, that's called a periodic function because p is called the period. And so if you add a certain amount p, or 2p, or 3p, or 4p, if you add a certain amount that periodically repeats itself, this is especially true of like sine functions and cosine functions and tangent, the trigonometric functions. Then all you have to do is kind of graph one period and then copy it for all the other periods. So that's a kind of, I guess it's a kind of symmetry. X-axis symmetry is basically if you put in the opposite of f of x and it ends up the same. So if you make y negative and it comes out the same, then you're going to have x-axis symmetry. Of course, that's not going to be a function because it won't pass the vertical line test. Lastly, symmetry. So those are all the symmetric. So we have y-axis symmetry, origin symmetry, x-axis symmetry, and then a kind of periodic symmetry, as it were. Okay, so we've done domain, we've done intercepts, we've done symmetry, and now asymptotes. So again, a horizontal asymptote, dotted line going horizontally, is going to be some number L where as x approaches infinity, the function's going to come to some L. And this is the previous video that I did on infinite limits. Vertical asymptotes, of course, happen if, as the limit x approaches a, the function goes to infinity. Often, vertical asymptotes appear when the denominator approaches 0. You can't go there. So asymptotes, we have domain, intercepts, symmetry, asymptotes, slant asymptotes. In this particular section of Stewart are introduced slant asymptotes. This would be like if a line is an asymptote. It's not horizontal or vertical. It's a slant asymptote. But one way to know this is if the degree of the denominator is 1 higher than the denominator, then you're going to have a slant asymptote. Of course, if you can put it in this form, also you'll have a slant asymptote. You can see mx plus b is simply the equation of a line. So basically, this is saying that the limit as x approaches infinity, the function approaches this line, and therefore that you're going to have a slant asymptote. Okay, so intercepts, domain, symmetry, and now asymptotes, and the increasing, decreasing test, ID test, increasing, decreasing. So this comes in the 4th chapter of Stewart after the chapter on forming derivatives. So if you know how to do a derivative, take the derivative, and then what are the intervals where the derivative is positive? Because if the derivative is positive on a particular interval, then that means it's increasing on the original graph. By the same token, if the derivative is negative on a particular integral, then you know that the slope is negative and that the original graph is decreasing on it. So this gives you a sense of increasing and decreasing, which can help you graph. And of course, related to this is maxima and minima. Maximum, minimum, plural, maxima, minima. So you find the critical numbers. What are the critical numbers? Critical numbers are, for example, where the derivative is 0. That's a turning point if the derivative is 0, right? Because if the derivative is 0, that means that the slope is 0, which means that it's either turning from increasing to decreasing, or it's turning from decreasing to increasing. So you have a turning point. You have a maximum or a minimum point when the derivative is 0. Now, of course, another kind of critical number is where the derivative doesn't exist. So you're going to have an asymptote or an open spot in the function at that particular point. As I said, if the derivative goes from positive to negative at a particular critical number, it's a maximum. By the same token, if it goes from negative to positive at a critical number, then it's a minimum. Okay, I'm not going to remember all of them. We've done domain, we've done intercepts, we've done symmetry, we've done asymptotes, we've done increasing, decreasing, and now we have maxima and minima. So related is the concavity. Concavity means, is it concavity up or is it concavity down? Here we're talking about the second derivative. If the second derivative is greater than 0, it's concave up. If the second derivative is less than 0, it's concave down. And of course, inflection points are points where the direction changes. Well, there you have it. These are all little hints to sketching graphs, and of course, sketch in the rest. And all I have to say is just do it. So there you have it. Some tips on graphing functions and equations that aren't functions even.